Okay, so just to kind of clarify, I had a boatload of technical difficulties yesterday. These are my days sometimes. So I had the video that we took first hour, and then I had trouble uploading it anyway. It's a long story, but somewhere along the way, it disappeared, and I can't find it anywhere. So I don't know if I deleted it or whatever, but I couldn't find it anywhere, and I spent way too much time trying to find that. So uh, in the event that that happens again, hopefully not, let me just show you the backup plan. So if you can't get to the actual classroom video, there is an alternative, and that is if I'm gone to this is Canvas now, and of course module one. And so if you scroll down to the bottom, and I'll do this as long as I can keep up from week to week, then you'll see here, this is, oh, we have a visitor.
Mr. Sheehan, I'm so sorry to bother you. Can I bug you for 30 seconds?
Yeah,
please?
hold on. Here, I'll let them.
I apologize. Everybody.
I'll bring in a guest lecture for a moment while we talk. I think it's gonna come up. Oh, there it is. They'll probably be asleep when they come back.
Video, we're going to talk about functions, section 1.1 in our book. But before I do that, I want to talk a little bit about this class in general and our kind of philosophy on how we're going to try to learn. And it's referred to as the Big Four in AP Calculus circles. And we're going to use the same kind of philosophy that is used in AP Calculus. That is, topics that we are discussing, we want to understand graphically, numerically, which for us means many times tables, analytically, which is how probably most of the math that you've done in the past has been done, things using formulas, equations, and so on, pencil and paper things. And then fourthly, verbally, which really means in words. That is, can you explain what you're doing? Can you justify why what you're doing is correct, and so on? So you probably have quite a bit of experience in the analytical parts and in quite a bit in the graphical parts. Typically much less in the numerical and the verbal parts. So those are things that we will talk about a lot, and we'll try to get more comfortable and more familiar. So we'll see that in today's lesson. So let's talk about functions. And first, let's come up with our definition for what a function is. So we're going to say that a function is a rule that takes certain numbers, as inputs, and assigns to each input value, exactly one output value.
I'm pretty sure that Jade signed up for a condensed AP course.
And the output is a function of the input, we say. The output is a function of the input.
Yeah, because usually people, if they're taking this kind of courses, they only take like 3 total.
Okay, so let's take a look at some examples of what this looks like. And so I'd like you to do this and put this stuff into your notes, and feel free to pause at any point in time. And what I'm going to do here is we're going to look at, try to understand graphically what we mean by what is a function and what is not a function. So I'm going to ask the question, which of the following graphs represent functions? So which of the following graphs represent functions? And then the harder part, perhaps, is why or why not. Can you explain why something is a function and why it is not? So I'm going to put down 6 different examples of graphs. At that point in time, you might want to pause the video and work those yourself and see if you can come up with which ones you think are graphs and why or why not. And then once you have gotten a chance to do that, then if you start
that
with
was
the video
boring, huh?
again, I'm going to explain
Sorry, punish
which
you like
ones
that.
are functions.
So there's Ariana and Megan. They're going to join our class coming here from Whiting. Great souls that they are. So you can see how these guys folded that into thirds. You see how those guys cleverly did that? You grab the dark marker of your choice and just put your name on one of those. It'll probably take me till Christmas to figure out what everybody's name is, but I'll work on it. Okay, so the idea is, this is my backup plan. So I tried to create these videos that are, and I'll put them in the support materials part. So, there was week 0 last week, here's week 1, and kind of what happened there. So on the video, it didn't come up. So when that happens, or even if you just need it, at some other time, if you need to access that, like maybe you want to get started on your homework and the video hasn't come up yet, even though it may hopefully come up, you can jump to there. Or what I'm going to try to do, and I don't think I did on these very first ones in this chapter, what I'm going to try to do is work different examples on that video than I do in class. So sometimes, the way it goes is that when you see it one time and maybe you think you get it, or maybe you even knew in class you didn't get it, but to see it a second time with a different problem worked out might help clarify it. So it's just a resource there if you choose to use it. Okay? And notice also there is a quiz that you need to do online at some point today on the 6 Ps. Okay, so that one you're just going to have to get on to Canvas and do that. Okay, I'm going to try to see if I can go back to, no, that's not what I want to do. Didn't mean that. I'll go back here to where we are back live and in person, I think. Yep. Okay. Questions so far on the mini disaster that we had yesterday? Okay, and options. So we got questions from the homework. Anything we would like to see done there? I'm going to take a little bit of time here. I'm going to try to stay disciplined, and as we go through the year, I will try to kind of reserve maybe 15 minutes for what we do to start class and answering questions and stuff, and then start the lesson so that I don't run out of time at the end. But the nice thing is, if I do run out of time at the end, I will say, oh, you can go check out that video in the support materials part of Canvas, and you can, click on that little dot and move it to the end where you can see the last maybe example or 2 or whatever I didn't finish in class, so you can still get the instructional piece. What I'm going to try to do too is to be a little more disciplined and restrict how much time I answer questions, try to get through the lesson, and then if I have time at the end, I can answer more questions or we can do some more practice problems. But we'll see how that goes. Yes?
Can we talk about 41 on the homework?
So 41 on the homework. Do you know what that is?
It's the one about the world record times and like on a year.
Okay, let me see if I have that here in my book. my book has been shredded. So 41, if I can find it. Okay, yep, so I'm going to read it here real quick. I'll just pull that page out of my book. I don't recommend you doing this to yours. So on 41 it says, since Roger Bannister broke the 4-minute mile on May 6th, 1954, the record has been lowered by over 16 seconds. And then we have a table that you're going to have to check out there that shows the year and the times of new world records. And so, was there any, there's a bunch of parts to this, A, B, C, and D. Was there any particular one or any on all of
The
those?
ones about like which one is a function of the other, because like it said that one thing, I don't remember which one was a function of the other, but like we didn't really get that.
Yeah, okay, so let's see. So A is the time a function of the year? So is time a function of the year? And then I think B is going to be the other way around. Is year, let's say Y, function of the time. Okay. So remember, this is what we were trying to talk about a little bit yesterday on the video, is that we said that for something to be a function, then for each input value there can be only one output value. And then we looked at different ways that we had to interpret that. So we said graphically we can use the vertical line test. And we said that numerically, which is what we have here when we have a table, we're going to say, you're kind of looking for the negative. Is there an input that gets matched with more than one output? So what to say, is T a function of the year? So so the record time, let's see, so if T is going to be a function of the year, then this is going to act like the functional value. I don't know if I want to say maybe X. And then the year is going to act like the X. So the question is there a year that is there an input year that has more than one output, a world record? And the answer, I believe, is yes, because the world record was lowered more than once in some years. Does that make sense? So according to them, what we talked about, since we have an input here that has more than one output, that's our one-to-many, that means that is not going to be a function. So T is not a function. The world record time is not a function of the year. So that answer is going to be a no. Does that make sense? Now, the other way around, if we say, is the year a function of the world record time? So now you look at those different world record times. Okay, those are the input values. Is there a world record that is matched with more than 1 year? And I think no, right? Because once the world record occurs, that's happening at a moment in time, and that's going to go with that year. So then that satisfies our one input. Each input gets paired with exactly one output. And so this would be a function.
Okay.
So you have to really kind of tease it out and think about that. And I had a couple people already in this morning asking questions, which is great. If you got questions, ask them. And there is a lot of words and language in here that's really tough to tease out. But that's part of the challenge. And that's why we have to practice it. Other questions? Good.
43.
43. So 43, I think says, okay, so I'm going to erase this one and put up 43. So on 43, it says a price increases 5% due to inflation. So I'm going to just say it increases 5% due to inflation. And then after that is reduced 10% because of a sale. So express the final price as a function of the original price P. So we're going to say, how do I want to say that? Ooh, still got it. Did you see that? A lesser athlete couldn't have caught that. So we're going to say maybe the final price is going to be some function of t. So, or some function of the original price. So here is, I'm going to just call this p sub 0 the original price, which we don't know. Okay, but that's not a variable. Whatever that is, it's a number. Okay, now, then what we're going to do is inflation is going to increase that by 5%. How do we show that?
1.05.
Ah, very good. So it's not just times 0.05, right? That's the increase. So there's kind of two ways you could do that. You could say it's the original price plus the increase of 5%. Or we jumped right to it. If you factor out that p sub 0, you're going to get 1 plus 0.05. And so the efficient way of writing that is going to be to say the new price is 1.05 times p sub 0. That's the increase of 5%. You with me? So this now, well, I'm going to put there. So I'm going to say that's going to be 1.05 p sub 0. So that now is our, that's going to be the price after inflation increases it by 5%. Now what we're going to do is put it on sale and decrease that price by 10%. How do we show the decrease of the price by 10%?
Multiply by 0.9.
Excellent. So we're going to multiply by 0.9. So if it's decreased by 10%, we're going to pay 10% less than 100%. We're going to pay 90% of that. And so that means we're going to multiply that by a 0.9. Does that make sense? So then you could, I mean, you could leave it like this. This is now our function of time. It's not really a function of time. That's just going to be our price. So asking for a function of time. Express the final price as a function of the original price. So I guess if this original price changes, so I guess we're going to allow that to change there.
Could it be f of p?
So then it would have to be, right, so let's call it f. I like that idea better because otherwise we get too many p's in there. It gets very confusing. I like that. So it's a function of the price p. So whatever that price is, we're going to first increase it by 5%, then turn around and decrease it by 10%. Then we're going to pay 90% of that. And you can multiply that out if you want. Good. Other questions? All right. So I am going to now jump into today's lesson. And we're going to talk about rates of change. So this is now section 1.2 in our book, and it's going to be rates of change. So the expectation then, and I think everybody's there, we're taking notes on this. So anything I put up on the board then, I expect you to write down in your notes, and I'll check that again. Today is Wednesday, so I won't see you Thursday, and so it'll be on Monday. And we'll check 2 at a time. So the idea is, and I'm going to talk general here, and we're going to look at this in our different modalities. So we'll look at what does that mean in terms of a function represented as an equation or a formula. What does it look like in terms of a graph? What does it look like in terms of a table of values when it's given numerically, and so on. But I'm going to talk first just kind of general, and I'm going to talk in terms of a graph. So the idea here is if we have some function, whatever it looks like, and I have its graph. So maybe we know its equation, maybe we know its graph, maybe all we know is a table of values. Then a big idea in pre-calculus is an average rate of change. So whatever this may represent, then if we look at a particular time or value down here, and then we look at another one. So I'm just going to call that x of 1 and x of 2. Then this point represents the value of this function at that time or that value of x. And this point on the curve represents the value of that function or value at that time for whatever that x represents. So an average rate of change on this function is going to be how much did it change as we went from there to there. And so we are going to look at this as and you may have used this symbolism and notation in your Algebra 2 days, you may not have. We can call this down here the change in x, which is represented by this Greek letter delta. So part of my challenge in this class is to try to make you fluent in Greek by the end of the year. So that Greek symbol there is delta, so that's how we read that. You see it in fraternity row a whole bunch too. So that represents the change in x, and then this is going to be the change in y. So what we mean by the average rate of change of a function, and I'm going to put average in parentheses because the assumption is going to be in any pre-calculus class that when we talk about rates of change, we have to mean average rates of change. Now, it's a real big deal next year in AP Calculus that we will try to figure out how to talk about an instantaneous rate of change. But to do that, we have to learn some calculus, and we're not ready for that yet this year. So it's going to be the average rate of change, and we will talk about this so much that I'm going to be, you can fill in the blank, efficient or lazy, but I'm going to abbreviate it. So I'm going to call this the ROC for the rate of change. And it's understood that I mean the average rate of change. And so it's going to be that, so that rate of change, that average rate of change, is going to be the change in y over the change in x. That make sense? You call that something else. What's another name for that you called it in your Algebra 2 days?
Slope.
It's a slope, exactly. So that is the same thing as the slope, okay? And you may have learned it as y2 minus y1. That's the change in y over x2 minus x1. Okay. Nod your head if you have seen that before. That sounds familiar, hopefully. Okay, good. And I'm going to extend that a little bit more. And so I'm going to say that, let me even change colors again because I love having all these different colors. So if here I called that x1 and x2. Let me rename that and call it A and B. And then this y value up here, so if I put that y in there, that y value would be, what would you call that in terms of a function? Function notation.
F of A.
Exactly. That's going to be f of a, right? And this y value up here would be f of b. So, I mean, it's like we're taking something simple and familiar and trying to make it more complicated, but it's part of what I do. So another way of getting this average rate of change is, besides the familiar y2 minus y1 over x2 minus x1, we could call that using function notation f of b minus f of a all over b minus a. So don't get thrown by the notation, the function notation. It's a familiar, hopefully, idea from before. And this is an average rate of change. Okay, so when you hear find the rate of change, you're thinking, I've got to find the change in y over the change in x. I know how to do that, hopefully. And we're going to look at that in different modes. So we're going to talk about what happens when it's a graph like this. How's it going to look when it's an equation? How's it going to look when it's a table of values when it's given numerically?
So something's like a function of another variable, is it always the dependent variable?
Yes, and that's a great point. Yes, so this, we have used here x's and y's, and we kind of lived in that world most of the time in Algebra 2, but we want to broaden that, and so it's going to be always the change in the dependent variable over the change in the independent variable. Yes, good point. Okay? All right, so I'm going to give you a table of values here. We'll look at this numerically. So let's say we've got a lemonade stand here. Use your imagination. Back when we could do lemonade stands. So we're going to say that this is going to be the time, and this is going to be the number of lemonades sold. And I'm going to give you a table of values here. So I'm going to tell you time of day. So this is going to be like 9 a.m. and then this is going to be 10 a.m. and 11 a.m. and 12 noon and 1 in the afternoon, 2 in the afternoon, 3 in the afternoon. Okay? So there's our independent variable, the time. And the number of lemonades sold is business was slow at first. We didn't sell any. Still didn't sell any by 10. Business picked up by 11. We had sold 2. Now this is the cumulative amount here. So these numbers can't go down because we're not given any refunds on this lemonade. Okay, so at noon, we had then sold 5, and then 13, and then 17, and by the close of business at 3, we had sold 18. Does that make sense? So can you find I'm going to say find the rate of change, that is the average rate of change of sales of lemonade between, and then we'll do a couple of these to get the hang of it, between, we will say, let's say from 8 a.m. until 11 a.m. Or we'll go all the way to 1 p.m. So from 8 to 1, we'll cross over that noon time frame. So we're thinking average rate of change. This is going to be our change in y over the change in x. So the change in y at 1, we had 13, right? Minus at 8, we had 0. And so then do I just go 1 minus 8?
No.
It's not going to work, right? Because our time is kind of goofy here, right? Because of the way we count time. So we had to kind of rename this, right? So before we try to do this change in the t values, we need to reframe this. So we could either do like whatever they call it, 24-hour clock or military time, or we could just say, I'm going to call this time 0 because that's when our time started. That's when our clock's going to start. And then we have 1 hour increments. So now I can think of this as being something like that. You see the issue and how we're going to resolve it? I need nods of heads here. Okay.
Except then wouldn't 8 be -1?
Then would what now?
8 o'clock would be -1?
8 o'clock now is going to change to being, oh, not 8 o'clock. Ah,
Yeah.
I'm going to change that. That was my mistake. Thank you. Oops. See, I'm trying to blame technology when things go wrong, but I can't do that very well here. Yeah, I didn't want to go into negative time. That's a whole other issue. Okay? All right. So now that I fixed that, we can say 4 minus 0 for our change in time there. And so that's going to be 13/4. And you're fine leaving it like that. Or if you want, let's see, 4 goes into 13 3 times, and that's going to leave you with 1/4, which you could either leave as a fraction or you can make into a decimal, either way. What's our units going to be here?
Number sold per hour.
Number of what sold?
Lemonades.
Yeah, so it's always going to be the units of the y value or dependent variable over the units of the, or per the unit of the x value or independent variable. So in this case, that's going to be lemonades per hour, because time is measured in hours. And that's going to be something that you're going to be asked regularly, so to try to think about that. Okay, I think we're good on that. Let's go on and look at something graphically. So we're going to take a look at a function that is represented graphically. So I'm going to put my axis here in white. And since I have the pink chalk, I'm going to say that this is going to be 2, and we go 2, 4, 6, 8, 10, 2, 4, 6, 8, 10 along the horizontal. And then I'm going to find 10 is going to be about there. And I'm going to say that that's 10, 20, bold. 30 is up there. And we're going to call, this is going to be height on the vertical, height of an object that we are launching into the air. And I'm going to measure that in feet. And the horizontal is going to be time, and that's going to be in seconds. And then the actual curve is going to be I know some points on there, it's gonna be there, and 6 is gonna be way up here, and at 10, we're gonna be back down to here. I'm gonna try to connect that with something that sort of looks like a parallel, but you can use your imagination, something like that. Okay? So here's our function. Or is it a function? Is height a function of time? Ooh, we should ask that question. That's a great question. Is h a function of t? Yes or no?
Yes.
Yes, and what would be your argument? So if I said justify it, you would say,
it passes the vertical line test.
because we have it as a graph, we talked about last time, that we can invoke our vertical line test. So yes, and that would be because of the vertical line test. Make sense? Let's turn around the other way. Is t a function of h? Don't say it out loud for a minute. I want you to think about it and chew on it. And can you can you justify it? Hold on, I know you got it, Ron, and I want to see if anybody else is there. I think you got it too. What is your name?
Nora?
Nora. Oh, I knew that. Nora.
Hi.
Okay? And I think Nora's got it. Anybody else bold enough to volunteer an answer? Yes, no. You got a 50-50 chance. What do you think, Ben? Go on a limb.
No,
No, I agree. Why?
because like if you had time on the y-axis, then it wouldn't pass the vertical line test.
Yeah, and it's kind of hard to visualize a little bit. So how can we describe that with what we're looking at there? So we said that if we have our dependent variables on the vertical and our independent variables on the horizontal, you got to turn your head over there and look in the other room too, I think. Then we can use our vertical line test. Well, what's a simple version to see if we switch those around? It becomes a horizontal line test, exactly. So if a horizontal line intersects this in more than one point, then the independent variable is not a function of the dependent variable. So we can say no, and that would be because, I'm going to use that universally accepted abbreviation, because a horizontal line intersects the graph in more than one point. Okay? Makes sense? So it's a horizontal line test. Very nice. So in that case, you would be seeing that, you know, the independent variables, the input values are coming from the y, and this input value along here is matched with two different output values. So going back to our definition of a function, each input value must have exactly one output value. This would be an input value that has two different output values and therefore fails to satisfy that definition of a function. Okay, so good. Let's do, can we find the average rate of change between, let's say t equals 0 and t equals 2, and we can chew on that, and then I'm going to say the rate of change between t equals 2 and t equals 6, and then can you find the average rate of change between t equals 6 and t equals 10? So 3 questions there. I'm going to give you a moment on that. Feel free to compare your answer with somebody next to you. You can use a soft voice, but one that they can still hear through your muffling of the mask, and compare your answer. So try the first one and compare your answer with your neighbor. And if you don't agree, you have to have a distanced arm wrestling match to resolve it. Feel free to talk at this point in time. And include the units in your answer too. So are we getting agreement? So I put up on the board here. You can check your work with mine since you refuse to check with your neighbors. You shy people, you. I don't really believe you're that shy. So I use the function notation, h of 2 minus h of 0 over 2 minus 0. That's like our f of b minus f of a over b minus a. I'm going to try to push you out of that comfort zone of algebra 2 where you might have called it y2 minus y1 over x2 minus x1 and get you into more of this function notation stuff. And so the h to the height at 2 means we come over here to 2, we run up to the curve, and the height there is 10. And at 0, we had the height was 2. And so that's how I came up with the 10 minus the 2. And 2 minus 0 is 2. And so 8 divided by 2 is 4. And the units are going to be the units of the dependent variable per independent variable. So that's going to be feet per second. Okay, we okay with that? All right, so you're doing the second one. Try not to talk too loudly. Yeah, right. When you finish, you can check with what I've got up on the board. Do we agree or do we need to debate? Okay with that? Any nods of heads? Claire, we okay with that? All right, very good. Megan, we okay? All right here. Grace? Okay, so again, h of 6 minus h of 2 over 6 minus 2. H of 6, the height at 6, we read across there is that 30. Got to use your imagination there. And h of 2, we said earlier was 10. And so the 30 minus 10 is 20. And the 6 minus 2 is 4. And that's going to be 5. And our units are still feet per second. So last one, I'm going to go h of 10 minus h of 6 all over 10 minus 6. You okay with that? H of 10 is going to be how much? 10. And h of 6 we said was 30. And 10 minus 6 I think is 4. So we get a negative 20 over 4. And that's a negative 5 feet per second. So an average rate of change can be negative. It could be 0 also. Okay, so visually what's happening is this first one, what we found was the slope of the line between 0 and 2. So there's a visual that goes with that. So that average rate of change was the slope of that line that connects those 2 points on the curve. Does that make sense? So it's kind of a nice visual here. And the next one was the slope of the line between those 2 points on the curve. And then the third one was the slope of the line between those 2 points on the curve. Kind of cool? Try to contain yourself. Pace yourself. Okay, so let's talk about function notation. So we're going to do this now with our function given as an equation. And talk about rate of change, average rate of change there. So let's say that f of x is going to be x squared. And let's find the average rate of change between let's say x equals 1 and x equals 3. Okay, so we get to use our function notation here. Is nice. I'll give you a moment. You know what to do? Do we need help getting started? You could consult with that person that's like right next to you too. Just saying.
And I got -1 or 3 -1.
Oh, yeah.
Okay, I didn't give any units on this. So we all coming up with 4, hopefully? Anybody not coming up with 4? Okay, so, and I didn't give any units there, so I can't really ask for that. Okay, so I'm going to talk a little bit about increasing and decreasing. This is a huge idea next year. So we want to kind of at least plant the seeds. We'll talk much more about this through this year and especially next year. So I want to talk about increasing and decreasing functions. I'm going to give you a definition here. And then we'll try to take a look a little bit, maybe at some examples. So we say that f, a function f, is increasing. And I'm going to put in parentheses here. This is really a property on an interval. And so sometimes you may hear people say, the function is increasing at this point. The function is increasing at x equals 3. And we understand what that means, but really it's a property of an interval. So it's increasing at x equals 3 if it's really increasing on that little interval that contains x equals 3. So it's over a region there. So f is increasing if as x increases, f of x increases. These values increase. What in the world does that mean? Let's look at it visually here. So f is increasing if as x increases, f of x increases. So a function could be increasing everywhere if it is always rising from left to right. So a function that does something like that is said to be an increasing function. Because as x increases, as we go from left to right, that's what we mean by x increasing. Okay? The x values get bigger as we go left to right. Then the y values are getting bigger. So the heights of those are getting bigger. Then we would say f is increasing everywhere or on its whole domain. Okay? Question?
If it dipped below at one part, would it be increasing?
Save that question for a minute. Okay, I'm going to come right back to that because that is a great question that I want to talk about. But let me put decreasing down, then I'll come back because I'm going to ask you that question. So f is decreasing, again on that interval, if as x increases, f of x decreases. Oops, that's supposed to be the axis. So the idea here is as we move from left to right, as x increases, then the y values are going to get smaller. So a function that does something like this would be a decreasing function. So we can talk about a function that is always increasing or a function that is always decreasing, but as Nora was leading to there, what a lot of times we want to know is a function could be increasing on some intervals and decreasing on other intervals, and can we identify which is which? That is, what intervals is the function increasing on, and what intervals is the function decreasing on? So let me give you an example of that, because that's really more common. So let's see, I'm going to say our function is going to do this, something like that. So here's our function y equals f of x. And I'm going to give these important places here names, but I'm not going to give them number names. So I'm going to say that is A, that is B. We know that that's 0, x equals 0. That's going to be C, and that's going to be D, and that's going to be E. So I want to put some distractors in there. We may or may not need all of those. But the question then is going to be, or the questions I'm going to ask you is for what intervals, change colors, So first question is, for what intervals is f, and I'm going to say, I'm going to write out the word increasing, but this is another one where, we do this so often, and mathematicians being, you choose, efficient or lazy, they abbreviate that. So if I use this symbolism, that means is f increasing. Okay, now I don't have to write out the word increasing. I just put an arrow going up. Okay, that's implying that it's rising from left to right. Okay, so we want to know, where is f increasing? So when we look at this, the idea is it's going to be increasing where the curve is rising from left to right. So not here, because now it's falling, and then we get to here. Now as we keep going, it is rising from left to right. So along here, this function is increasing. Then it starts to fall again, so we've left that. So it's this region right here, this piece of the curve that I drew in purple is where that function is increasing. What we have to name it by is that interval. That is, we have to give the x values that generate that part of the curve. So your answer is going to be in terms of x, not in terms of y at all. Okay, so when you look at that, that's going to be along here. Okay, that's the part of the x-axis that generates that part of the curve when you plug it into the function. And a big question in AP Calculus is, do you include the endpoints or not when it's increasing or decreasing? And the answer is yes, if the function is defined there. So this point B right here is included in that part where as the x values get bigger, the y values get bigger. And so we would say, for what interval, we can write this two ways. In terms of inequality notation, we could say for b, less than or equal to x, less than or equal to d. Does that make sense? So that is inequality notation. That's perfect. If you answer that, that gets full credit. That's exactly what I want. There's also what's known as interval notation. I don't know if you're familiar with it or not. Some people really like it because it's a little less writing. So we could say from b to d, including the b and including the d, would be brackets b, comma, d. So this means exactly the same thing as that. The bracket means you include it, and you always go from smaller to bigger. Okay? Now, second question then is, we'll say, for what intervals, or perhaps intervals, so I'll put in parentheses the s, for what interval or intervals is, and I'm going to use my abbreviation, is f decreasing. So I can write that symbolically with an f and a down arrow. Okay, well now I need a new color. Fortunately I have one. So now the part of the graph, it's going to be decreasing when the graph is falling from left to right. So that's going to be this part of the curve here, but it's also going to be this part of the curve there. And so we have two pieces, which means our answer is going to have to be in two pieces there. So we can say for, and I want to say for every from B to the left. Now, do I include B or not is the question. Actually, you do. And that's what really bothers people in AP Calculus. How can it be in both the interval where it's increasing, but also in the interval where it's decreasing? Well, remember, it's an interval. So is this part of the x values where as you go left to right, the y values are getting smaller? Well, right there, that is part of that interval. And so it is included both in the interval where it's increasing and in the interval where it's decreasing. So we could say for b, and we could say less than or equal, x, less than or equal to b. That is one correct way of writing that piece. I'm not done. And you could also say, if you want, you could say negative infinity has to be less than x is less than or equal to b. Okay, that's kind of a funky way of doing that. Can you see that down there? I'll write it up here. That's negative infinity less than x less than or equal to b. That's the same thing. That means the same thing as x less than or equal to b, but you get to impress more people that you've communicated, with that infinity symbol. It's kind of important. Now, in interval notation, you would say negative infinity, which you can never include infinity, to b, which is included. So you show the not included with a parentheses and included with the bracket. Then you can use the word or because there's more to it. And or means something very different than and in math. Sometimes in conversation we get it just from context. You know what I mean. Not so in math, so we use the word or. And then we're going to get this piece over here, which we're going to say, we could say is x greater than or equal to, so we're talking about this piece right here, x is greater than or equal to d. Or if you like, we could say d less than or equal to x strictly less than infinity. Kind of impressive.
Did you mean to write b is less than or equal to b?
Here?
No, on the other side.
On the other side? Oh. See, you said that and I still couldn't see it. Thank
Okay.
you. Yeah, now that's what I meant. Thank you. People watching the video are like, what? Okay. Or we could in interval notation, so somebody help me out. Oh, well, never mind. It's going to be d to infinity that way. All right, very good. Homework 3 is on the table. I'm going to stop the video.